Well, good morning and welcome to physics class. And we are continuing with relativity. We talked about Galilean coordinate systems. Now we're going to talk about special relativity, which of course comes out of Einstein's research. The other theory, which we kind of skipped over that, but it presupposed that there was a fixed universal reference frame. That was its assumption, that there was a reference frame that everything else was moving in. And special relativity says, no, there is no such thing. There is no preferred reference frame. It doesn't matter what reference frame you're using. There is not a particular special reference frame. And so there are two assumptions. This is very significant for special relativity. Two assumptions. First one, each law of physics has the same mathematical form in all inertial reference frames. We've already touched on that, okay, in Galilean approach to this, that the laws of physics were the same in all inertial reference frame. Remember, inertial reference frame is not accelerating. Now, the speed of this number two, this is the one that blows it. The speed of light in a vacuum is the same in all reference frames. This is the key thing. So you've got reference frames that are moving with respect to each other. When they're moving with respect to each other, the speed of light should either add or subtract. And he says it doesn't. It stays the same. Well, if the light stays the same, then what is relative? Well, what's relative is dimensions, masses, and time. And I just will comment, because people talk about relativity and talk about moral relativity. The key is there is an absolute in Einstein's relativity, besides the fact that it's a physics theory and not an ethical theory, which means they really don't have a whole lot of relevance. But more than that, there is an absolute. The absolute is the speed of light in a vacuum. It is the same in every reference frame. So there is an absolute standard about which everything else is judged. Okay, so on the first assumption, that the laws of physics are the same in every inertial reference frame, Einstein assumed that no physics experiment can distinguish between a reference frame moving at a constant velocity and a stationary one. Again, no acceleration, but if it's moving constantly or it's stationary, there is no way to tell from inside which it is. Okay? And the second assumption seems to run contrary to our experiences, which if you didn't already figure that out, I'm sorry, I went really fast over that. Okay, so in a Lorentz transformation, v is the speed of the object measured within the observer's frame of reference. So if you are observing an object moving, within your frame of reference, you're observing it moving. It has its own frame of reference, okay? It has its own frame of reference. But you are looking at it from your frame of reference. C is used for the speed of light in a vacuum, 3 times 10 to the 8th meters per second. And that's the reference point, because the speed of light is the relevant constant in all of this. So these are what they call Lorentz transformations. And you'll notice those are kind of ugly. Well, y and z are not, because it's not moving in y and z. But if it's moving in x, then depending on how fast it's moving, x and t get altered. And we're going to come back to that in relevant ways in a minute here. At normal speeds, v over c is a very small ratio. If you think about 3 times 10 to the 8th meters per second, something that's going in the, even thousands or tens of thousands, the fraction is going to be really small. And when when that fraction is very small, you get the same equations we had in the Galilean transformation. That's important, because one of the things with new theories is new theory should always reduce to the old theory in the old context. And it does. And a speed much smaller than c is anything less than 1/10 of c. So you've got to be going 3 times 10 to the 7th in order for you to be getting into relativistic speeds, okay? Relativistic speeds are those approaching the speed of light, so 0.1 c and higher. 10% of c may not seem like very much, but considering how fast c is, it is. Okay, so there are 4 interesting predictions that involve simultaneity, time dilation, length contraction, and mass increase. So, I know I went through that fast because we're going to go through them again. Simultaneity. If one observer says that 2 events in 2 places are simultaneous, another observer moving with respect to the first will not see the events as simultaneous. And they do a really cool thing with the boat and the lights. And if you're interested, I recommend you read that. I didn't include it here because they didn't include it in the PowerPoint, and I'm not I really need, if I'm going to do that right, I need a lot of time and diagrams and board, and I just don't have it. So you're going to have to take it on faith that because of Einstein's relativity, the Lorentz transformation, if one observer says, oh, these two things happened at the same time, another observer who's moving will say, no, they didn't. They happened at different times because the light will get to his eye at a different time because he's moving. Time dilation. This is really cool. Time dilation means that an observer perceives a clock moving with respect to him as running slow. So if you're watching somebody who's traveling at high speed, you're going to watch their clock and you're going to watch your clock, and their clock's going to run slower than your clock. And mathematically, it's been shown that the relationship is this. Looks really weird, but what you have is time equals time, but it's divided by this 1 minus v over c squared. And see, that ratio of the speed of the object to the speed of light is significant. The closer that ratio is, the larger that number is, and the more impact you get. And that fraction, 1 over the square root, is called the relativistic factor, or gamma. Okay? And if you do it that way, then you can replace that and you just get gamma. So that simplifies the equation, which is nice. It simplifies the equation as long as you understand what gamma is. And gamma will always be greater than 1, okay? Because it's a fraction. Because of the way we set it up as a fraction, it'll always be greater than 1. Oh, on your review, term number 1, number 1, the terms. Number 3, relativistic factor gamma is this, 1 over the square root of 1 minus v over c squared. Okay, so that's your on your review page. You want to fill that in on your review page. What happens to length? Well, if an object is moving with respect to an observer, its length along the direction of motion appears shorter. So if you were measuring it as it's flying by at high speed, if you were able to measure it, it would become shorter than what it would be if you were inside this, let's say, spaceship. If you're inside the spaceship, you measure it, you get one length. If you're outside the spaceship watching it go by and you measure it, it's shorter. Now, it's not an appearance. Okay, it says appears here. It really is shorter. And proper length is the length of the object as measured by an observer moving with the object. Okay, so that's L0 is the length by the person in the spaceship. And if you divide that by gamma, you get the new length. And this is only in the dimension parallel to the direction of motion. So if it's moving the x direction, which is what we're assuming in our equations, then only the x-axis will be affected. And it's noticeable only to an observer outside the moving system. So if you're in the spaceship, traveling very, very fast, you're not going to see any of this. None of this will be noticeable to you. If you're outside the spaceship watching it, then it'll become noticeable. Okay? Mass. The apparent mass increases with speed. So if you were somehow able to measure the mass of something moving at high speed, it would be more massive than what it would be if you were inside the spaceship with that object. And this is required for the conservation of momentum. Rest mass is our reference point, the mass measured by a person who's moving with the object. So if you're in the spaceship with the object, you measure it. And then if you compare that to someone outside the ship, the person outside the ship is going to be m0 over this, or gamma m0. Okay, so the mass is going to increase. It's going to appear to, it's going to measure as increased. Okay? All right, let's go to concepts on your review page. All right, number 3, time, mass, length, and simultaneity at relativistic speeds. Okay, number 1, or the first one, time. A rapidly moving clock, as in a clock that's on a spaceship moving rapidly, will seem to run slow. Each minute actually gets bigger. That's what it means by running slow. So you would measure 5 minutes, you'd look up and its clock would only move 2 minutes. Their 2 minutes was equal to your 5 minutes. Isn't that weird? Mass. A rapidly moving object measures more massive. So if you have a mass and it's rapidly moving, if you measure it, it will come out more massive than before. However, length gets shorter. A rapidly moving object measures shorter. It will actually measure. If you were to be able to measure, it would be shorter. So if you had a 50-meter rocket and it shoots by you and you measure it as it goes by, maybe use lasers or something to catch it as it goes by, it would not be 50 meters. It would be something smaller than that. And simultaneity, observers in different reference frames will not agree on simultaneity. And that's as far as we're going to go with that. We could go a lot deeper into some of these concepts. And if I had time, I would. All right, let's go to the math section of your review now. And number 1, the physics class has rented a rocket for the junior-senior trip. During the trip, the class reaches a speed of 0.300 c. If one of the students has a mass of 100 kilograms, what is his mass according to a stationary observer at this speed? So there's our equation. Okay. So we plug it in. M equals 100 divided by the square root of 1 minus 0.3c over c squared. Now the c's are going to cancel. C over c cancels. And I know my square root's a little weird. I apologize. They do a lot nicer square root than I do. 0.3 squared is 0.09. 1 minus 0.09 is 0.91. The square root of 0.91 is 0.9539. So you divide 100 by that and you get 104 kilograms. So their weight has increased. Their mass has increased 4 kilograms. Before we talked about going into space and you said your mass doesn't change. It does in this context, in this situation. Okay, next problem. If the rocket is 50 meters long, what is the rocket's length as measured by a stationary observer? So the equation, again, we have this. It's L equals L0 over gamma, which is L0 times that square root. That's 1. This gamma is 1 over the square root, so that's the square root in the numerator. So 50 times the square root of that, which is still the same as it was in the previous problem, except we multiply now 50 times 0.9539, so it's only 47.7 meters. So the rocket will lose 2.3 meters as measured by a stationary observer. Okay? Plug and chug, really, just with some really interesting results. Practical effects. Okay, speeds of 10 kilometers per second, that would be like 6 miles per second. The factor of gamma is that, which most measurements are never made to that level of precision. So the gamma is not going to have much effect at low speeds, even what we would normally consider fast speeds in our world. So what if one observer is stationary while another, the spaceship, is traveling at the speed of light? Okay, not close to, but literally at the speed of light. Well, to the observer in the spaceship, time in the space station is standing still. Okay? So because each minute gets longer and longer and longer and longer. When you hit C, it's so long, it's infinite, and it just stops. Time stands still. This is, well, okay, we're going to get back to this later with Humphreys and the black holes and white holes. Anyway, sorry about that. Got ahead of myself. The meter stick held a certain way has a length of 0. Remember, it gets shorter and shorter and shorter until if the rocket's actually moving at the speed of light, it's going to go to 0, which means it's going to disappear. You're not going to see it. And the mass of a bounced ball, for their example, seems to be infinitely great. Remember, the mass keeps getting bigger and bigger and bigger. So eventually, the mass of it is going to be infinite. Now, I will just tell you, this is actually not going to happen simply because as you get close, as the mass increases, the force you need to make it go faster gets greater because of F equals ma. So as the mass gets greater, the acceleration inherently gets less. And as it gets less, then it eventually won't. You would never be. It would be you would need an infinite amount of force to push it that last little bit. Einstein's theory was that nothing can ever go that is slower than the speed of light could ever go the speed of light. Nothing going the speed of light can go anything but the speed of light. And anything faster than the speed of light can never go slower than the speed of light, which is a really interesting thing because as I understand it, if you were to have objects traveling faster than the speed of light, they could be existing in our universe, and we would never interact with them because we're both lower than the speed of light and they're above the speed of light. Not sure about that, but that's what I understand. Okay, is this real? Does this make any sense? Does this work out in experiments? The answer is yeah. They can actually do something with muons. And muons are subatomic particles that fall through the atmosphere. Muons have a very short half-life. Their half-life is 2.2 microseconds. but they travel very fast, 0.9 c. And so if they've actually measured how many muons come through the atmosphere, a muon in a half-life travels about 600 meters. So every 600 meters, half of the muon should disappear, but they don't. They actually travel farther. And the reason is because time is traveling differently in the muon than it is outside the muon, because the muon's traveling so fast. And so it actually travels farther than it should during its half-life. And they've actually measured this. The other one is the clock paradox, and that is basically if you have two spaceships, and they did this with airplanes. What they did this was with airplanes with very, very, very sensitive clocks. They take two jets and they fly them opposite directions, so their relative speed is double the speed of the jet. And I know that's not very fast compared to the speed of light, but if you're having a clock which is sufficiently precise, which is what they're using are extremely, extremely precise clocks, they're able to actually measure this, and they actually were able to prove that this worked. Okay? I will just throw in here because it's fun, the twin paradox. Because of the way time works, if you had twins and the one twin gets on a rocket and he takes off in his rocket and he flies at almost the speed of light, really, 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 really fast, and he travels for, let's say, 20 years, and he gets back home, he'll discover that his twin brother's 40 years old, 40 years older than he was when he left, whereas the twin in the rocket's only 20 years older. Isn't that weird? Okay. The applications of special relativity, and I'm just going to be honest with you, I'm not sure how these two connect, but they do. Mass can be converted into energy. This is nuclear power. And 1 gram of matter theoretically contains 9 times 10 to the 13th joules of energy. E equals mc squared. They didn't even put the equation in the PowerPoint. E equals mc squared. You're multiplying the mass by the speed of light squared. So it's a huge number, and you produce a huge, huge amount of energy. They say that one gram of paperclip could produce $2.5 million worth of energy. Now, in real life, you can't convert the whole paperclip. You're only converting a very small fraction of the matter into energy, so you don't get that much. But that's why nuclear energy is so powerful, is because you're converting matter into energy, and that's a huge conversion. All right, well, this finishes the second section. We got one more section, a lot fewer slides in the second section, but several review questions, and then we'll be done with relativity, and we'll move on to quantum. Anyway, have a good day.